Hello everyone, my name is Flavia and I'm going to talk about middleware support for generic and flexible actuation in the Internet of Mobile Things. We are part of a research group from PUC-Rio, which is a university in Rio de Janeiro, Brazil. Shaditon defended his master's last year, and this paper is about the main topic of his work. Felipe is an undergraduate student, I'm a postdoc, and Professor Marcos Endler is our supervisor. In recent years, we have observed a rapid growth in the Internet of Mobile Things, with deployments in a vast range of areas that go from smart homes to healthcare and industry, among many other sectors. Very often, these IoT systems include sensors and actuators. We call these devices actionable smart things, or ASTs. These devices have the capability of changing their state or performing changes in the environment where they are. Here we have a few AST examples, such as smart bulbs, smart locks, robots, and even drones. Today, most of the implemented IoT systems are hardwire and device-specific, which means they cannot handle new deployed devices on demand. It also means that they can handle the unbounded and dynamic set of device types and models that exist. Another important characteristic we can observe in current IoT systems is that both devices and gateways have the potential to either move autonomously or be moved by someone or by some other device. To support this type of demand, our research group proposed the ContextNet middleware, which is a scalable middleware for mobile Internet of Things devices. It is composed of services in a core network, which is executed in a cluster or cloud. It supports edge computing through the Mobile Hub, which is a software that runs on any Android device. The M-Hub runs several services that enable discovery, connection, and interaction with BLE sensors and actuators. It provides 5 main features, which is the communication with gateways, the discovery of mobile things that are around the M-Hub. It has a fully fledged complex event processing engine, which allows filtering, summarization, data aggregation, among other operations. It allows contextual information enrichment by using the local sensors and resources of the smartphone that is running the M-Hub. And it also has local energy management, which allows the M-Hub functions to work according to battery levels. So, for example, it adjusts the frequency of communication with the gateway depending on the battery level. Here we have an overview of ContextNet. It is a middleware with a three-tier architecture. The first part is the SDDL core, which is a P2P network of stationary nodes running in either the cloud or a cluster and interacting with the M-Hubs. The M-Hubs are the second part, and they are running on mobile devices supporting Android. Data and commands are forwarded to and from the SDDL core by the M-Hub, and the microservices connection service and S2PA are responsible for that. The third part are the IoT devices, or ASTs, with sensors, actuators, and BLE beacon capacity. Our work proposes a mechanism to deal with the heterogeneity of actuation devices, which is caused by the large number of existing manufacturers and standards. We do so by abstracting the complexity of native protocols. This way, we allow developers to create their own set of high-level commands and enable actuation through these high-level commands. This is an overview of the architecture of the solution we propose in the paper, which is an extension of the ContextNet middleware. This extension consists of 2 new microservices, the MACT and the SOM. MACT is a microservice running inside an M-Hub, which has 2 main tasks. It requests our drivers for near devices, and it translates a high-level command into a command in the native protocol. SOM is a microservice running on the ContextNet core, and it works as a repository for AST drivers. It keeps a connected table to inform all participants about which AST is available at which mHub. Besides that, we propose to also use drivers to abstract the native protocol and define a subset of high-level commands that compose the application Actuation API. Our goal here is to allow a user that is anywhere on the globe to control a smart thing through the internet. To accomplish this, we have the system where a client connected to a ContextNet gateway sends commands to an actuator that is connected to an mHub somewhere. So the communication should pass through SOM in the ContextNet core and through mHub with an active MACT to be delivered to the smart thing. All messages in this process should be the MACTQuery type. Here's an example of an MACTQuery. It is a message protocol that we developed to help the actuation process through ContextNet. It should be used by the client to send a command to an actuator, and also used by SOM to send drivers to MACT. The MACT works as a central element in the mHub architecture. So here, from the perspective of the MACT, we have that it receives MACT queries from the mHub through the connection service microservice and sends commands to the generic actuator that models the AST, which then translates those messages to the mHub microservice S2PA. As a processing node of the ContextNet core, the SOM communicates through the universal DDS interface, which is the SDDL layer, in a pub/sub pattern. For this reason, messages to SOM must be identified with a tag, which is the same tag that SOM is subscribed for. The SOM contains a register of all connected ASTs, which is the connected table, and it is associated with a driver repository. This way, SOM can associate a single driver with many ASTs. There are two cases that occur during the process of discovery of an actuator. Here's the first case. The mHub discovers an actuator. Then the MACT tries to find a driver for it internally. If the driver is already loaded, then MACT tries to connect to the actuator. Then, if the actuator sends a confirmation about the connection, the mHub sends a message to SOM to notify it about this connection. In the second case, the mHub does not find a driver internally. So you must request a driver to SOM, who replies with the requested driver. When the MACT receives the driver, then it can connect to the actuator, which replies, and then that is relayed to SOM. This diagram shows a complete actuation sequence. It starts with a client requesting a list of actuators available. This request is sent to the gateway and is received by SOM in the cloud or cluster. The SOM replies with a list of connected devices, sending the mHub ID of the gateway where the actuator is connected to. After the client receives the list of objects, it is able to send generic commands to the actuator. The command is sent directly to the mHub, where the actuator is connected to. So the MACT in the mHub translates this generic command to the native protocols and sends it to the actuator. Here is a sample of a driver. All drivers must have an implementation of the connection function. So this function will be called by MACT when mHub finds the AST. A driver may also have local functions to help developers with more complicated tasks, for example, checksum or encryption. And finally, all other functions in the driver represent high-level commands for the AST. So here we have an example of that. These functions receive just one argument, which is args, And this is a table with the parameters needed to execute a command. In this example, we have the roll command, which is for the BB-8 robot. It receives the parameters regarding the speed, the direction where it's heading, and a state, which is either 1, so it can continue to move, or 0 if it has to stop. Here's a comparison that highlights how our work is related to other similar investigations. It evidences the need for a driver or any other mechanism that can describe the particularities of each AST and assist device interoperability. In addition, we note that despite allowing the inclusion of new devices in the application, Data Bonnet and McCain implemented a repository mechanism of drivers. However, their repository is limited to the gateway, unlike SOM, which keeps the repository with the drivers available for all accessible gateways. We created an example application to both register and control ASTs in order to verify the feasibility of our proposal. And in the first experiment, we tested the scalability of our approach by evaluating how the number of devices registered in SOM influences the time it takes for new AST devices to be discovered by mHub and then to become available for actuation. Here in the graph, we can see that the increase in the number of devices registered to the SOM is growing a lot faster than the time it takes for the AST to be ready for actuation. Even if we compare the best case and the worst case within the standard deviation, we know that while the number of devices increases 10,000 times, that the time to be ready will increase by less than a factor of 2. So this can be considered to scale really, really well. In the second experiment, we tested the latency. That is, the time it takes for a command to travel from the customer to the AST device. To evaluate the latency of sending commands, we used our application to control an air conditioner. So we established 3 different scenarios to evaluate if the implemented version of MACT could handle the commands while stressed with other client nodes sending messages simultaneously. So we have a scenario with 1 client, a scenario with 2 clients, and a scenario with 4 clients. We see here that in all cases, the latency of most of the messages are up to 200 milliseconds. The highest frequency of messages was in this interval between more than 100 and up to 150 milliseconds. More than 90% of the messages will fall here until 415 milliseconds. However, we have this right side here, which further illustrates how there is a very low number of messages with high latency that goes up to 500 milliseconds more or less. The presence of these measurements can be explained by the fact that we are using the 2.4 gigahertz band communication for communication, and that is used by several wireless devices. So messages end up colliding more. But overall, the large majority falls here up to 500 milliseconds. In conclusion, we have that our proposal is an extension of a middleware to support mobile IoT actuation. The main contributions of this is that it can be modified in execution time and allows the development of APIs for actuations. It only depends on the functions available in the registered driver. We created an example application to test that, and it allows the registration of several devices while only slowly increasing the time it takes for them to be ready for actuation. And commands can be sent with up to 5 milliseconds latency in a scenario of up to 4 clients. If there are any questions, please email them to Sheraton at sheraton@gmail.com. Thank you.